Hello everyone, welcome back to the workshop. Today I'm going to be reading through a very interesting book that I think many of you will enjoy. Now, I did gloss over a lot of these pages, but still it's going to be a long and boring read with little spouts of very interesting information every once in a while. So if you skip around during this video, I don't mind at all. The book is Goddard Goddard, Tools That Go and Go. It's a milling cutter book made in 1947. Very interesting. Let's get into it before this video gets any longer. Hello everyone, welcome back to the workshop. Today I have a very interesting book to show you all that I bought recently. It's called Goddard Goddard, Tools That Go and Go. It's a catalog of milling cutters made in 1947. Now in 1947 we didn't have CNC and we didn't even have tape-controlled machines. The Milwaukee Maddox that made dies for the big Mesta forging presses, they weren't even really an idea as far as I know. Everything that you see in this book was done with a different design philosophy in mind, with different requirements than what we have today, and in different methods than what we do today. So let's get into it. First chapter is going to be on solid high-speed steel milling cutters, then high-speed steel inserted cutters, carbide tipped milling cutters, reamers and boring tools, then thread mills. Yes, they did have thread mills in 1947. They were far more common than you might think. Railroad cutters, solid high-speed steel milling cutters for special profiles, and then maintenance and engineering data. We might not go over the maintenance and engineering. A lot of this I am going to just gloss over, as I said, because a lot of it is just price lists. This is Catalog E. Just price lists for things, but there are interesting things like this excerpt on helical milling cutters. Helical plane mills offer extremely free cutting action due to a high helix. These mills are made with a 52-degree helix angle and a 10-degree undercut. Hand of helix is optional. For milling soft steel or brass, this mill can be run at high speeds and feeds without leaving high feed marks, and produces an exceptionally smooth finish because of its progressive shearing action. The high helix prevents the cutter from hogging down when entering or leaving a cut. As a result, it is ideal for light cuts on thin, springy pieces or intermittent cuts in frail parts. Stuff like that is interesting to know because many people, they don't know whenever they see a cutter that looks like that. They don't know what it was used for or why they made it with such a radical design. Over here it says these cutters are designed for taking heavy cuts up to a ½ inch and more. The undercut teeth and high spiral combined with the adequate chip room promotes free cutting action and smooth finishes. Left-hand spiral of the cutter reduces chatter and directs the thrust against the spindle bearings. Stuff like that's also very interesting. As it cuts, it pushes against the spindle. I didn't realize that. I didn't think about that. And that's why I'm going over this book with you all. Some more price lists. Staggered tooth side milling cutters are designed for deep slotting and keyway cutting. They are so key-seated that any two cutters of like diameters having the same number of teeth can be interlocked. The teeth are undercut with alternate left and right hand spiral, and they have the drag at the end of each tooth to cut away. Side teeth only have a slight degree of clearance and are slightly concave to avoid bugging. This construction eliminates side thrust, promotes free and clean cutting action, permits high tables feeds, and produces smooth, accurate work. When wide slots are to be milled, we recommend staggered cutters. Side mills are for general tool room work and general operations, such as straddle milling and shallow slots. Heavy duty straddle mills, that one's kind of boring. This is really interesting. They'll take staggered milling cutters and gang them up to produce some wider cutters. Now this action, this almost herringbone effect, or not herringbone effect, but herringbone shape of the cutting teeth reduces chatter and produces a better finish as far as I can tell. Brown and sharp T-slot cutters with staggered teeth. Half-side mills are the ideal tool for straddle milling and milling onto a shoulder. The spiral and undercut teeth produce a smooth cutting action. Deep gash sides and peripheral teeth provide ample chip space and allow many regrindings before salvage is necessary. These cutters are standard in both right and left hand and will be furnished with sharp corners unless otherwise specified. I have a couple of these style of cutters, and I didn't really know what they were specifically for. I didn't know why they didn't just use the standard sort of either this design where the teeth are cut on both sides for the side milling cutters, or this style. So these are meant for straddle milling. Slitting saws. Plain type for ordinary slotting and cutoff operations. If you're watching this video, you probably know what that is. Metal slitting saws with side clearance. Side clearance is provided to avoid galling and distant undercuts. Promotes free cutting. Saws should never be driven by depending on friction of collars, as slippage will cause breakage. Always use a hardened key extending into collars on each side of the saw. For heavy service, saws should be equipped with reinforced hubs. So, a lot of people say that you should only drive these guys with just friction. Goddard Goddard disagrees that you should use a hardened key. Personally, I do a bit of both. I've had many of these just shear the key. But that's mostly because of user error. Staggered tooth or... so this style is only made in 3/16 and up because it's impractical for anything that's thinner than that. Special metal slitting saws. So this style of saw is most efficient for deep cutting of copper, brass, and aluminum. So these ones are for softer steels. Woodruff key seats. Everybody knows what a Woodruff cutter is. More Woodruff cutters and price lists. Single angle milling cutters. Those are single angle milling cutters, have teeth on angular faces and on the side adjacent to the largest diameter. These cutters are available either in right hand or left hand with included angles of 45 degrees or 60 degrees and double angle cutters. I'd like to get some of these, mostly for milling dies, 45 or 60. Shell end mills. These cutters are designed for both face and end milling operations and will fit standard shell mill arbors. See listing at the bottom opposite of the page. Shell end mills are standard with either right hand cut and right hand spiral, or left hand cut and left hand spiral. See tabulation. Morse taper end mills. That looks like a scary combination. An end mill on a Morse taper shank. These, I believe, are mostly for boring mills. Now, I wouldn't really use that in the modern day because the shank, there's nothing to pull it up onto the into the spindle. But of course, if you want to use one, I'm not going to stop you. Two-lipped end mills. These end mills are standard with either right hand or left hand spiral, and it doesn't tell you what they're for, besides the obvious. Helical end mills are most suited for milling cams or similar profile work. They are capable of milling both sides of a cam path, while with one of a cam path with good finish at one pass. When operation requires the cutter to bottom the mill, can be supplied with shallow end teeth as shown in the illustration. Helics double end mills. Helics end mills. Some more end mills. Ball nose end mills. Special end mills. That looks like a serious cutter. End mills are used for a wide variety of milling operations such as end milling, profiling, slotting, and surface milling. All go-and-go standard end mills are made with high spiral curved undercut flutes and the ground tooth face to produce well-curled, free-flowing chips, all instrumental in promoting higher production, smoother finish, and greater tool life. Yeah, that's all fairly standard stuff. Concave cutters. This is obsolete, so I gotta go to this page, I guess. Although the whole book is obsolete by this point. Physical dimensions of standard concave cutters were recently revised by the Metal Cutting Tool Institute to cope with present-day milling machines. Bore diameters were enlarged to permit the use of arbors, which will utilize the greater power and higher feeds available in modern equipment. Cutter strength was also increased proportionally, resulting in the new cutter diameters listed below. That is really, really interesting. So essentially, the Metal Cutting Institute decided that they were going to change the dimensions of concave cutters to cope with newer machines that were stronger with more horsepower. I wonder what the differences are exactly. Let's go. The biggest one, 1 inch diameter circle, 3 1/4 inch hole size is 1 inch, whereas on here 1 inch hole circle is 4 1/4 inches in diameter instead of 3 1/4. 1 9/16 inch wide. This one doesn't tell you the width. Hole size here was 1 inch, and here it is 1 1/4. Number of teeth 10. Number of teeth 12. And the price jumped up about $8. But they weren't too happy about that, but stronger cutters cost more. Convex cutters, I'm guessing that these, these ones were revised for the exact same reason. These ones are stronger, the newer ones are stronger, newer. Corner rounding, again, more changes. This one's obsolete. I don't know why they decided to print the obsolete side. Maybe it was just to get the information out there that these ones were revised and you can't really get them anymore, and so you got to go to the new ones. Roller chain sprocket cutters. These cutters will have form-relieved undercut teeth and will maintain their true form when ground with the same undercut as marked on each cutter. The distinct rake of Goddard Goddard sprocket cutters promotes freer cutting action than the radial tooth types. Cutters listed are not carried in stock, ordered by number only, symbol number only. So these are all of the roller chain sprocket cutters. Helical gear hobs, these ones are discontinued, I guess. All sorts of information, just hub run out, dimensions, and diameters, diameter run out, just all kinds of information. Gear hob nomenclature, enlarged tooth or enlarged view of hob tooth. Information like that is why I got this book. Inserted blade milling cutters. Economy is an ultimate factor with Goddard Goddard insert cutters because of long grinding life provided through blade adjustment, low cost of blade replacement. So these were just cheaper to run hard. It's cheaper to run them very hard. Inserted shell mills. Kearney and Trecker had a very interesting design for this style of cutter. They were called the Fullback Cutters. I'd like to get one of those someday, or a couple of them in different sizes. Maybe I will find a book on those and review those. Staggered tooth slotting cutters. So if you see any of these and you wonder what they were for, they're just slotting cutters with an inserted tooth. And of course, horizontal milling cutters with the same design. Stridle Mills and the W series blades. If you ever see these guys, then that's what they're for. Cutter maintenance. Radial blade adjustment can be made in steps of 1/16 inch as peripheral wear requires. Axial setout can be varied as desired. Blade adjustment is accomplished easily. Drive out the wedge as shown. Make make desired the adjustments and reset the wedge lightly. Blade overhang on sides and periphery should not exceed blade thickness, so the overhang shouldn't exceed the thickness. Before resetting the wedge, dip in mixture of white lead and oil to avoid corrosion. Drive the I had a big 12-inch Goddard Goddard cutter, and I tried to drive the wedges out. It looked very similar to one of these. Let's see. I went back a little bit too far. Let's see, we're on page 69. It looked very similar to this guy over here. It was 12 inches in diameter with a big 2-inch or maybe a 3-inch arbor hole. I tried to drive out the wedge as shown here, and that thing would not go. It had been sitting in the scrapyard for a long time, and no matter how hard, no matter how big of a hammer with how small of how big of a punch, it would not drive any of them out. I think there were 16 teeth. It wouldn't drive a single one out. They didn't put white lead and oil on there to prevent the corrosion. Drive the wedge out gradually, working around the cutter, first with light blows, then with heavy blows to equalize body strains. A good check to see if you have driven in the wedges evenly on an arbor-type cutter is to mount it on a stud. If the wedges have been driven in evenly, the cutter will turn freely on the stud. So an issue with these guys is if you drive them in too hard and you're not very even with your pressure, it will warp the body of the cutter. That's a good thing to know. I didn't know that. And of course, inserted angle cutters and radius cutters and all sorts. This is a very interesting setup. 15 inches from side to side. That is a lot of teeth, and I bet that cutter did a lot of work. That probably took a fair amount of horsepower to drive. I bet that that's not a 40 taper spindle, but that's definitely a 50. This here is the style of milling cutter that I had, that I bought, that I eventually sold for more than I bought it for. These ones here, just standard information. You have 3 lines of cone face type mills for complete coverage of facing applications. Cone type, how to maintain your cone type face mill, a fixture for driving the wedges while it's on a shank. Giant spirate cutters. I bet these things did a huge amount of work. Rod profiling cutters, taper, reamers. Railroad cutters, that's what these are. Meant to remove a high amount of material. Here's them in action on boring mills for radiator shell dies, roof dies. This is how they used to make dies for the automotive world and really for many, many applications. Spirate end mills. Giant bolt-on end mills. If you have to bolt something to your face, it's a pretty high horsepower cutter. Here's a giant one. 20 inches from side to side, plus another couple of inches for this width of the cutter. That's for, it doesn't say what it was for, but I'd imagine that's for some kind of a saddle, for maybe a milling machine or something else. Spirate cutters with all of these individual teeth. These aren't, if you'll notice, these aren't just a single big spiral. There's 1, 2, 3, 4, 5. There's 5 cutters in that one little section. And they still got them to get a really nice finish. How to grind your spirate cutter so that all the teeth are in line. And carbide tipped cutters. Actually, I think the 12-inch cutter that I had that was too big for my mill. It was probably a carbide tipped, but these are all very, very similar. The only difference really is the design of the shell mill and the insert itself. All milling applications should be engineered. This demands a knowledge of cutting material, the material to be cut, type of cut, and operating conditions. Carbides are no exception. Recognition of their properties in milling has made possible greater production, more pieces per grind, and better finishes at lower costs. Carbides are very brittle, 90 to 92 Rockwell A, 76 to 80 C. They retain their hardness under high cutting temperatures, permit high cutting speeds, however their brittleness limits the maximum speed consistent with the overall machining rigidity. Excessive vibration, chatter, or impact will break out the cutting edges rather than wear or use the carbide. Carbides have high compressive and low tensile strength, which limits the amount of positive rake for the easily machined materials such as aluminum, and necessitates the use of negative rakes for machining hard steels. In addition, carbide cutters with cutting edges have small included angles and sharp points, carbide cutters with cutting edges having small included angles and sharp points as yet are not practical. So this is just talking about how you use carbide cutters in 1947. High-speed steel was still the king, but carbide was just starting to come out. In fact, carbide did a lot of work in World War II for war production. Stridle Mills, big old face mills. This one looks similar to the one I had. That looks almost exactly the same size. A 12-inch with a 2.5-inch bore, $189. Now I paid about half of that to buy it, and a little bit more than that to sell it, or I got more than that when I sold it. Some more carbide insert mills. This is all standard stuff. The cast alloy blades with the brazed on carbide teeth. How to maintain them. Pretty much the same as the high-speed ones. More information on them. All sorts of different kinds of carbide inserted cutters. They did have carbide inserts at this point. An 8-inch diameter, 0.3125-inch wide carbide tipped side mill. A giant gang mill. These were very, very common, especially with the big horizontals, because you could do an immense amount of work with a big gang mill, especially when you have high horsepower and lots of parts to do. More carbide tipped milling cutters. These aren't inserted. These are just tipped. Carbide tip solid body gang. I'm guessing that's for the saddle of a mill. That's for the, not saddle of a mill, but saddle of a lathe. And I'm guessing that that's for the bed of a lathe. I know there's an illustration of a gang that was specifically used for a lathe. Big hogging reamers. Same design really as the face mills, but just extended out with a different purpose in mind. Shell mill arbors for hogging reamers. Expansion chucking reamers. Expansion reamers. These reamers look very similar to their face mills. Blades. Starting to come to the end of the book. Hollow mills. This special hollow mill is used for finishing stud and cheeks on a locomotive link saddle plate. The body of the tool is drilled with oil holes in the front of each blade to deliver coolant. The pilot bushing on the tool is creating a reservoir. See opposite page for machining setup. That's very interesting. They use this to basically finish a boss on a big locomotive part. Goddard Goddard, the company, made all sorts of tools for all sorts of applications. I imagine this is just a fraction of what they really did. This here is for finishing out multiple faces on a bore. Special reamers for high production applications. Tapered reamers, things like this. Face mill, or not face mill, but spot facers, sorry. It still mills a face. Concave reamers for putting radii in a body. And thread milling cutters, multiple thread milling cutters. So thread mills were actually fairly common for a wide variety of applications, mostly very coarse threads and tapered threads. Straight gash cutters, spiral gash cutters for external thread milling, 4.5 inch API, 5-tooth tool joint pin end. The oil industry, in which Goddard and Goddard multiple thread milling cutters have been used extensively for many years, has provided a challenge and proving ground for the development of this tool. The problem of production thread milling long coarse pitch threads on heat-treated alloy steel tool joints to the very exacting requirements of this industry is a supreme test for a tool and speaks volumes for what can be accomplished with Goddard and Goddard thread cutters. These cutters can be supplied in practically any thread form with an accuracy shown on the table 164. When ordering, refer to blah blah blah. So these were for those oil pipes. You see those tapered threads that are very coarse on an oil pipe for oil drilling? Well, Goddard and Goddard used to make cutters specifically for those. This is cutting the dies for a roll threader on a big milling machine with special cutters. If you see these guys, and they almost look like taps, well, those are probably thread mills. These almost look like hobs, or even roughing mills, some of them. Heavy duty cutters for railroad shop and similar work. So this is a different design for a big slab mill, different blades that can be ground down to a certain point and then flipped over. So you get two blades, or twice the life out of the same blade. Slabbing a locomotive end rod. That is an operation. This type of cutter, developed about 1925, is still made on request. Blades are carried in stock for servicing many cutter bodies in use. Standard sections are made in 4-inch wide widths, and any number of these sections can be combined to make a complete cutter. Sections and blades are standard in either right-hand or left-hand spiral, so that the complete cutter can be built up by using all one hand of spiral or herringbone type. Whenever possible, it is desirable to use an equal number of right and left-hand sections in order to equalize thrust on the spindle. So, this big cutter here, they have half of them are right hand and the other half are left hand. That makes it so that all of the force is not going in one direction. It kind of pinches the part, pinches everything up, and prevents any side thrust. Or prevents an excessive amount of side thrust. Gives you a better finish and less chatter. Spirate cutters, another thing on them. Spirate rod profiling cutter at work. Note the long, well-curled chips. All sorts of vintage, but still very, very interesting cutters. Now that is a reamer. That's a big old reamer. They look just like slab mills. Hogging reamers again. Adapter type, taper shank type. Big taper reamers. These are actually mills. I believe they're called arbor mills. Basically long end mills that are supported at each end, one end on the spindle, the other end on an arbor support, for milling or slab milling large parts. Goddard and Goddard cutters, helical mills. This mill was originally developed by the Goddard Goddard company sometime back in the railroad shops. So Goddard Goddard actually developed helical slab mills. Adapters, pilots, helical end mills, box cutters. This cutter is designed for milling shoe and wedge faces on locomotive driving boxes where an extremely husky tool and high cutting efficiency is required. That's a plane mill, or mill planer. If there are any parts of this book that I gloss over and just didn't talk much about that you are still interested in, let me know. I will do another video at request on a specific part. Crosshead cylinders for the crossheads on, I believe, locomotives. Special milling cutters. Now this is the section I've been waiting for. These special milling cutters, they get ridiculously complex. Typical hacksaw gang. So this is a gang for milling hacksaw blades. I need to get me one of those cutters so I can make my own. A special type of gang saw made up of 15 1-inch sections, 4-inch diameter by 2-inch hole, interlocked with teeth progressively staggered. Teeth are made intermittent type. These gangs are made to include as many as 38 sections at time. So 38 sections of 1-inch milling cutters, 1-inch wide. So that's 38 inches. That's a big milling machine and a lot of work to be done. Relieved cutters, special form for cogs. These guys. This is a photo that I think is very, very interesting. This is, I believe, a roots blower. This cutter mills a 13-inch diameter rotor having 3 lobes at a 31-degree helix angle. Due to this high helix angle, the entire form on the rotor is produced by generating action. Yeah, this stuff like this is how they made complex parts. They would have large cutters with very special forms in them, spending many hours getting this just right. And then they would mill the whole thing in one shot on a very rigid and very strong machine. Milling turbine blades, I'm assuming for, what is it? Big steam turbines on Navy ships. I believe those came out during World War II. Milling the cheeks of a counterweight on a crankshaft. Note the wide chip breaker in which give intermittent cutting action and break up a long chip. This is a gang milling setup for straddle milling the ways in a lathe. So if you see the ways on a lathe and you think, how do they do that? Well, they did it in one shot on a big milling. They did it in one shot on a big milling machine with a very big gang. Another gang of profile cutters. If you have a lot of milling cutters and you don't know, you want to have a job where you need to use a bunch of them, you can just gang them up, use them all at once. This provided your milling machine is big enough and your cutters are sharp. More special milling cutters. Heavy duty slab milling. Special profile milling cutters. More special profile milling cutters. That looks like the way on Adam's new lathe. Adam from the Small Town Machine Shop got a new LeBlanc, and that looks strikingly similar to the way, the front way on his new lathe. More special milling cutters. how to grind them, pointers for good milling, machine, rigidity, must be in good condition and adequate size for the job, tighten the gibs to remove all play, see that backlash is kept out of table feed, taper seat of spindle or adapter, must be free of burrs or nicks, taper seat of the spindle or adapter must be free, flywheels are in form of rigidity because they supply inertia when needed, mount as close as possible to the cutter. Arbor must be of proper size. Cutters must be of proper size. Basically just common sense. Speeds and feeds. Exact recommendations are difficult because many variables must be considered. General, keep the cutter rotating when setting up or use plastic feelers. Never disengage the cutter when the feed is still engaged. If possible, do not return cutter over the surface just milled. If not possible, keep the cutter rotating until off the work. Climb or plunge cut whenever possible. Air blasts or suction to help chip disposal. To get the maximum service out of a good milling machine and good milling cutter, properly harness the cutter, drive it at correct speeds and feeds, and properly anchor the work. To obtain continuous high production and maximum cutter service, never allow a cutter to become excessively dull. When the land wears on the cutting edge is 1/32 of an inch wide, the cutter is generally ready for sharpening. Flood the work with coolant and all materials except for cast iron. We do not recommend the use of coolant when milling with carbide. More calculations. Analyze the job. Calculate horsepower requirements. Calculations. Copper or magnesium for your surface feet, 600. For high speed, copper, 500. Cast steel, stainless steel. All kinds of information that I got this book to get. Feet per minute peripheral, 1 inch, 699, 175 feet per minute. Cutting speeds. Climb cutting versus conventional cutting. Sharpening. Now this section is going to be incredibly useful whenever I get a tool and cutter grinder. I'll be able to refer to this for different information that I need, such as angles and how far to go. More sharpening. Cincinnati tool and cutter grinders. Standard and best in the business. With many gashed cutters, they would sit there and use a special form that has the lead on them. I didn't know that. Especially for smaller cutters. Shell end mill drives. Mill drives. Jarno taper shanks. National standard taper shanks. All of the information for taper shanks. Brown and Sharp tapered shanks. Morse taper shanks. Helical end mill holders. Helical end mill holders with National Machine Tool standard shanks. Decimal equivalents. Why would they print out a page of decimal equivalents? Hardness conversion. Just a huge amount of information. Acme screw threads. Information for Acme screw threads. Pipe taper threads. 4-thread chamfer in a die. National form threads. SIE. Sharp V threads. ASME standard threads. And lastly, Whitworth and British Associates. A huge amount of information covered in a single book, mostly on milling, but with all sorts of different information. I know that this video was long and rambly and was kind of boring probably, but if there are any specific chapters in this book that you would like me to go over, or specific information, then please let me know. This book is incredibly it's neat. And with that being said, thank you for watching till the end. Please like and subscribe if you enjoyed this, and have a good day.